I think I'm ready.
Okay, here we are. So yeah, so I thought I'd just start by giving a kind of summary of what you said last time, and then you can maybe don't interrupt me too much at first, and then it'll be pretty well. I don't know if it's quick. You don't need to. Otherwise, you should.
Okay.
I imagine you'll have lots of stuff to say.
Okay.
So sort of starting from a basic idea and developing it more carefully as we go. So you can think of a principal G bundle over some space X. Sorry, I'm going to give all these letters.
Sure.
The functor F from the category rep G of representations of G to the category, for example, vect X of vector bundles over X. And what that is you form the associated bundle of any representation. I guess I forgot to write that.
I was gonna. I really like that buzzword associated in there. So add that in there somewhere.
Yeah. So this is a way of thinking of the associated bundle construction, a preliminary sort of way. And so, but we're thinking of this functor as going from some category of some kind to some other category of more or less the same kind, although vector bundles is not quite as nice a category as representations of G. But that whole way of thinking makes you think of F as giving a model of a theory in some doctrine, a model of the theory. So you think of rep G as the theory or the syntactic category of the theory. So basically the abstract entities, representations of G become, quote, concrete entities, namely vector bundles over X. And so you were polishing up this idea. And so first, to make the context of like what this kind of categories that both rep G and vect X are, to make it more precise. And then you discover that vect X actually isn't quite the right thing. But so that's one thing that we're going to do, but as part of that, we'll sort of go more algebraic and think of groups as giving commutative Hopf algebras. So basically the algebra of functions on the group. And principal bundles, we often think of them as torsors of a certain sort. So anyway.
I always have to stop and think about it. I mean, I think you got it exactly right. It's algebraic functions on the group.
But when you think commutative Hopf algebra, then that lets me know which way we're doing it. So that there are two famous Hopf algebras associated to a group, one of which is commutative and the other of which is co-commutative, and this is more the algebraic geometry one, whereas the other one is more like co-algebraic geometry or something like that. Right. Yeah, the algebra of functions on a space is how we go from geometry to algebra in this approach. So then what we'll do is define a general concept of torsor for any commutative Hopf algebra. And well, we're going to take a fairly high-powered approach, as I indicated. So we're going to pick a field K for our use in algebraic geometry, at least for now. We're going to work over a field. And then the kind of category that I was alluding to will be symmetric monoidal co-complete K-linear categories. So that kind of category is called a doctrine. A kind of category is called a doctrine. And this particular doctrine is symmetric monoidal co-complete K-linear categories. Rep G is such a category. Category of vector bundles is not actually, because, for example, the vector-vex category of vector bundles, it's not even an abelian category. It doesn't even have all equalizers and co-equalizers. So the way that the algebraic geometers deal with it, as you mentioned, is to go to a larger category of quasi-coherent
But you really, I think it's worth, for technical purposes, emphasizing that the version of co-complete that we should use is locally presentable. Because I think that really helps to make the whole subject much more rigorous than it would be. At least for me, it makes it much more rigorous than it would be otherwise. I don't understand the more general co-complete category.
Oh, okay. Well, that
locally
thanks.
presentable is really easy and nice to deal with.
Okay. So,
locally presentable means that it's co-complete in a sort of adjoint functor paradise way.
I'll have to ask you more about that in a second.
Okay.
I don't know if I would, but
Okay, sorry for the interruption, but
mixed up about some things about that. But
okay. Of course, yeah, there's.
I get mixed up. Well, anyway, I won't say. So the idea is then that we, instead of working with our group G, we work with a commutative Hopf algebra H, and then the category of, instead of working with representations of G, we work with comodules of H, and the category of comodules of H is a category of this kind that we're discussing.
Yes.
And so we call it a theory. And then we define a torsor of H to just be a model of this theory. So we're doing.
I also often say that it's the syntactic category of a theory, but maybe it's better to say it's a theory,
Yeah, some people, like in Levier theory land, will talk about the categories being a theory. Yeah, so I guess I've inherited that attitude.
Right.
But the main conceptual trick is we're sort of identifying principal bundles with torsors, but then we're defining them, i.e. torsors, to just be the models of this theory, instead of saying that a principal bundle gives you a model of some theory, but just say it is the model of the theory. And then there was a digression where you pointed out that we could generalize this even further by working with Hopf algebroids. I'll just say this junk. So that you like to think of that as giving a certain kind of notion of stack, which simultaneously generalizes the concept of space associated to commutative algebra. So when you have a commutative algebra over a field, you think of it as a space called an affine scheme. But then there's also the notion of a group associated to a commutative Hopf algebra, which is an affine group scheme. And so commutative Hopf algebroids are including both of those. Okay, but we didn't really do anything with that.
Well, this simultaneous generalization idea, it puts the both things living in the same context, where you can interpret one of the theories into the other, and that's like really, you can interpret a theory of one into a theory of the other kind.
Okay, so maybe we're actually doing that somehow. Yeah, I guess we sort of are. Yeah, we're actually doing that now. If you think about it carefully.
Yeah, let me see. It's promoting, relationships of some kind by getting everything.
So we are going to now start with a commutative Hopf algebra and then look at models. Think of it as giving a theory, namely its category of comodules, and then look at models of that. And then we get to choose where we look at models of that. Okay, but now I'm going to do.
Yeah, did you say kind of backwards? The really fun one, at least to begin with, is when you interpret the theory coming from a group into the theory coming from a commutative ring. That's where you
That's what I was trying to say. That's what I was saying.
Okay, it sounded backwards, but okay.
I think that's almost what we're about to do in a second here, although I go down to a special case, so it may be obscured. So
okay. Sorry.
But I think you're right. I agree that that's the fun one. So I don't even, well, maybe the other one's fun, but it's so weird. I don't even want to think about it.
Right.
So now doing an example of this business. So we'll start with a finite group G. We're going to turn it into a commutative Hopf algebra. H, which is just, in this case, just K to the G, made into a commutative algebra by pointwise operations and getting a Hopf algebra structure because of the operations in G. So then we can talk about torsors of H as models of the theory I mentioned. So a torsor of H is, we'll call it a G-torsor over the field K, I guess, in this case. Or I'm going to do that anyway. And so, okay, what the hell is it? Well, a G-torsor over K is going to be, well, here I describe it in a fancy way, like following the rules. It's a model. So it's a symmetric monoidal colimit preserving K-linear functor from the category of representations of G to something, to some C, which is some other symmetric monoidal co-complete K-linear category. And what I didn't do in this little summary is unravel that systematically, perhaps in the case when C is vect, for example. But I believe that if you do unravel what that means, you get something nice. Well, and unfortunately, we focused on, or fortunately, or whatever, we focused on the case when our group G was Z mod 2. And so in that case, a model of this theory is just a, I guess it's just a Z mod 2 graded vector space. Let's see, is it a Z mod 2 graded vector space or is it a vector space with an, it's a vector space with an action of Z mod 2, I guess. Is that right? Yeah.
Well,
I mean, I know those are the same thing.
So it seems like it's a Z mod 2 graded vector space.
Oh, not just that though, right? Yeah, sorry.
I think it actually ends up being like a Z mod 2 graded commutative algebra. Am I saying that right?
It should be a commutative algebra, yeah, because it's a model of this commutative Hopf algebra. It's a commutative Hopf.
Yeah, yeah. It might be. It might be.
I'm
trying to say. Actually, maybe that is what it is. A Z mod 2 graded commutative algebra. I was going to say it's a Z graded commutative algebra, but with a favorite invertible element in grade 2, I guess. But having that favorite invertible element in grade 2, that makes it into really a Z mod 2 graded commutative algebra, right? Because it says you can just wrap it around that, you know, grade 2 becomes grade 0 by virtue of the favorite isomorphism between grade 2 and grade 0. Am I saying that right?
Sounds about right. So what's the upshot? You get a Z mod 2 graded.
Let's see. Okay, wait a minute. I'm still not saying things right. So what are we trying to describe here? We're trying to describe what the torsors work out to be. So yeah. So in this case, it ends up being a Z mod 2 graded commutative algebra, but with a special property. These are great questions. Maybe I should wait to say more about this until it's my turn to talk. But
yeah, well, I know, but well, yeah. So this is fine. So I guess I'll guess that the special property is that it's, so when you have a Z mod 2 graded commutative algebra, you get a map multiplication going from grade 1 tensor grade 1 to grade 0. And we want, let's see, we want that to be, I don't know if this is everything we want, but we want that to be an isomorphism, I think.
Yeah, yes. But I think we also want each grade itself to be an invertible
Right. Yeah. So where's that? We do, but where's that coming? The way I'm imagining it is that, like,
I mean, at this point, where it's coming from is that we're claiming that if you analyze what this is, what this category, this representation category, what is its universal property? Its universal property is that it does that. But we have a lot of calculation and thinking to do to figure out why it is that that representation category actually has that particular universal property. And we've only stated the universal property in very sloppy ways so far, but we'll try to make it more precise.
yeah. So, okay. So anyway, it's good that I did this, because I'm actually, there's like tons more things to think about than I even noticed.
Yes,
So,
but the summary, but nevertheless, the summary is great. But go ahead.
Okay. So and so then we were, well, I really left out. So what we were aiming to do is to think of quadratic extensions of the rationals as z mod 2 torsors over the rationals. I just wrote k, but I meant k equals the rationals, and then checking that that's really a valid understanding, and checking that such things are indeed classified by square-free integers, which is actually part of the thing that we did more carefully than almost any of the rest of this.
Yeah.
Okay, so that's all I wanted to say, and yeah.
Okay. So so this sort of philosophy that you've just summarized here, I tend to call this the Tanakian philosophy. Tanakian can mean some different things, but this what you're describing here is what I think of as the Tanakian philosophy of algebraic geometry or mathematics. And as far as how affine algebraic groups fit into this Tanakian philosophy. So, I mean, yeah, we mentioned the idea that these theory morphisms or theory models that we're talking about, they are these functors of associated vector bundle nature, approximately speaking. And I just want to emphasize that, when I first ran across that use of the terminology associated, it sounded very kind of like subsidiary or something like that. Whereas in this philosophy, that's the central thing. The associated thing becomes, the whole focus and starting point of everything. So it's not subsidiary anymore. And so it's like everything else is associated to it rather than it being associated. So I mean, we were just kind of fumbling over the issue of exactly how does this particular syntactic category formed by the representations of this commutative Hopf algebra, exactly how does it have this universal property of giving things that we might call principal G bundles in some sense, according to some definition. Like I say, we were fumbling over this because there's so many different ways of thinking about it. I think that's one of our excuses for fumbling over it. But let's try to say some of the, instead of blurring all these different ways together, let's try and single out some of the very rigorous ways of thinking about this, pretty rigorous ways of thinking about this. So let's see, maybe at this point I should try to.
Yeah, sure. If you want to write in, yeah, that's fine.
All right. So how do I do this? Share screen. Okay, that's set up correctly now. You can sort of see my.
Yep.
So yeah. So let me try to give one fairly rigorous definition of what a G-torsor is, and this will start in a pretty general context, but then we'll really apply it to the context that we're interested in. So what am I trying to say here? So it's like I'll start out doing this for like abstract groups or something like that, but very abstract groups. So like we'll work for group objects in a very general sort of category. So supposing we have, let's see, supposing we have a group G, and supposing we have an action of a group G. We can make sense of that in pretty general context. So what am I trying to say? We have like X, and it's acted on by G. And, the action is a morphism, and it's various. I mean, I didn't say everything. There's a kind of action associativity and things like that, but yeah, this is what an action looks like of a group. And a G-torsor is just going to be a special kind of G action. The G-torsor is going to be a special kind of G action. And so how's this going to work? Don't tell me yet. Let's see. So I mean, what I want to say is something like that. In a certain direction, it's invertible. You can divide or something like that. So what are we saying? We're saying that you can, what does a group action do? It starts out with, I mean, we have group elements and points. So let's call them transformations and points or something like that. I'm trying to think of what terminology I should really use.
That's fine.
I'm going to call them, I'm not sure this is right. I'm going to call them like points and displacements or something like that. So the way the action works, you start with a point, you apply a displacement, and it displaces it to a new point, a different point, possibly different point. And that's the action. So it's going from, the points, Cartesian product, the displacements to the points. And now for it to be a torsor, what kind of invertibility do we want? Don't tell me, let me think. I want to say, so, I mean, this displacement, you can think of it as a sort of kind of distance or something like that. Well, is that right?
Well,
Right. I mean, by thinking of it as a distance, we're already suggesting the kind of invertibility we want, right? We want to be able to start with 2 points and ask what was the displacement or the distance between them. What was the what is the distance between them? By which we mean, what is this displacement that gets you from one to the other?
Yeah.
And this is, typically a very non-abelian kind of distance, a non-commutative kind of distance. The thing you need to get from the first point to the second tends to be the opposite of what you need to get from the second to the first, the inverse. So what are we saying? We're saying that in addition to this, there's a distance or displacement map that goes the other way. And what is the well, right, we could follow our nose and figure out what's the commutative diagram to say that these two things fit together in the right way.
Yeah, I like to write it.
What?
I like to use like elements of these things and write like x divided by x prime.
I wish I could just, we got to work this out better so we can both write on the same page.
I know, yeah.
I would like you to write that right now. So what are you telling me to write?
That second map.
Yeah.
Send the pair x comma x prime to the group element x over x prime.
Right. Well,
it's you have to be careful because it's a non-commutative multiplication. So you have to learn what the rules are for. I'm just saying that like the rules that you're trying to write down, they're sort of comprehensible if you, to me, if you write the action as like a multiplication operation and the displacement D thing is a division operation.
Oh, with notation like that. Right. But then I get confused about the backslash versus the forward slash.
Yeah, no, it's true that you have to.
Yeah, I wish you could write. Let me write something here. So what I want to say is that
Diagram too, yeah.
yeah. What I write, I'm right. I want to like write something sort of like a commutative diagram or something like that. So I want to say that we have pairs of points, and we have pairs consisting of a point and a displacement, and these should be equivalent to each other. Right. And it's sort of like by integration and differentiation or something like that. Right. This is sort of like,
Well, that's nice, yeah.
you know, I mean, I'm calling this D and I'm calling this A, but that's not quite the right syntax, but it's something like that, right? It's like
I think in both cases you sort of carry over this, it's like 1 times D, or the pair 1D and the pair 1A. That is the first element of X just sort of stays there.
all right, can we try to write down with you using the notation that you were suggesting what we were doing? So like we have like X1 and X2 over here.
Yeah.
And what do they go to?
So I think it goes to like, well, I could reserve the right to change my mind about the details, but it's like X1, comma
the distance from X1 to X2.
yeah,
You would
so
write as a division thing.
yeah, so there's probably something like X2 over X1. The reason why I say that, yeah, say X2 over X1. I have to worry about the left right
Sure.
baloney, but there's also like preliminary baloney to worry about. And then going back, it's like X comma G, X1 G, goes to like X1 X1 times G1. So this way you at least notice that as far as the first component goes, these are inverses to each other. That is, if you started out with the pair starting with X1, you go back and forth, you get back X1. So at least that part's, so all the action, oh, that's a really bad one. All the stuff is going on in the second coordinate. And then you are saying that like X1 times X2 over X1 is X2.
Say that again. What are you saying? What?
To get these to be inverses,
Oh, yes.
you need this equation.
Yes.
You will write for me, which is X1 times X2 over X1.
Yes.
Equals X2.
Equals X2. That's in one direction. You can do the other direction.
Okay, let's see the other direction. What did I do? First I divided, then I multiplied. So the other direction is X1 times G1. X1 times G1, nope. Well, X1 times G1, whole quantity in parentheses.
Oh, X, okay.
That little
sorry.
The quantity X1 times G1.
Yeah.
Divided by X1.
Divided by X1, yeah.
Is G1.
Is G1.
So I think we may not have optimized the notation for how the division goes. That like if you
right,
like we'd write the division on the left instead of on the right. The way.
So one of them should be the other kind, the other direction of slash. I don't know.
Both of them. I'm more just we're
oh, okay, yeah, maybe both of them should be. Yeah, okay. I don't
so
know.
You see, if you like move this, the thing that's in the denominator over to the left of a fraction, then it would all look incredibly beautiful.
Okay, but I don't even know how slashes, it sounds like you're saying slashes have a very natural orientation to them, and I'm not sure I understand that yet. I don't
Maybe I'm
want to.
gonna steal the controls just for a second, and
Okay, go ahead.
people who don't know what we're talking about.
Yeah.
So I was just, I unfortunately, yeah, this is really bad because now I can't see what you wrote, but oh well. So
Right, good. Let's try, go ahead, try just keep
yeah,
going.
I will. So I was just saying that, like, if we had the good way of writing, if we'd used the better way of writing division,
Yeah.
we would do something like this. So here, so this is like x2 divided by x1, but
Yes.
to the right. Or sorry, I don't know. No, sorry, whatever that's called.
Oh, so are you telling me that it looks like a nice associativity or something if you do it correctly or something like that?
Yeah, it's sort of like this thing is like canceling this thing right next to it. This is like in the denominator. And then the other one is
Yeah,
just like
okay. Okay, yeah,
x1
okay, I have a vague sense of what you mean when you say
times
that you don't
g1,
have the,
and then we divide by x1 on the same side there.
yeah,
So that way things are just like canceling things that are right next to them, and
yeah.
which is like suitable for a non-commutative.
Okay, yeah, so I admit that I didn't have it optimized in that particular way.
But it's no big deal. Yeah.
Right,
Okay, that's all I wanted to say. Yeah.
okay,
Yes, you have to
And,
grab it again. I can't.
right. I'm just trying to get back here. So, yeah, so I think this is the main thing that we need for a torsor, but I think this doesn't quite do it in general, because isn't it true that if X is empty, that
Yeah, then it's yeah, then you get these maps.
So
By the way, I'm gonna interject something. So I
Yeah,
did
go
an
ahead.
in-category cafe post about,
Yes,
so this is like a joke. So people are always talking about the field with one element,
yes,
but you should also think about the group with no elements, and which is like not really related at all as far as I can tell. But there's a Levere,
Yeah.
there's a Levere theory whose models that are non-empty are groups, but then it also has an empty model.
yes,
And the way I thought of it is that you formalize, they're different. I mean, it turns out that there's like a completely general procedure for any Levere theory to like get a new one that has the same models together with the empty one, which is what I learned.
plausible. Yeah, go ahead.
But my way of thinking about it, which I like in this example, which I like better, is that you formalize a group in terms of a multiplication operation and a division operation, which are inverses to each other. And then you don't state the existence of the identity, because the identity element you can just formalize as like anything divided by itself. So somehow the axioms imply that anything divided by itself,
Right.
the same thing, no matter what that is.
Yeah, that sounds vaguely familiar. Like I should remember that. Yeah.
And so then you get the usual concept of group, but also allow the empty group. And that sort of makes me feel a little clearer about this funniness about that we're encountering right now about torsors, that here you've almost gotten the usual concept of torsor, but there's also the action on the empty set is also counts as a torsor.
Yeah, but somehow in this context, it still bothers me. Like I don't really have the right thing yet, because
Yeah,
I mean, the only way I can think of at the moment to repair this little glitch is to rely on the doctrine being somewhat richer or something like that. Like maybe I want to say something like that. Maybe I want to say something like that. I want to give the displacement or the distance map D. I want to give it some kind of, by the way, right? We've been saying all these things. You can think of D standing for displacement, distance, division, But also it's like an internal Hom, which unfortunately doesn't start with D as far as I can tell. Right, these torsors, they're a special kind of enriched category, enriched over G, thinking of G as a discrete monoidal category. Not sure why I just threw that in. That's not really what I was trying to say, but there's all sorts of fun digressions here going on. Okay, so what was I trying to say? What was I supposed to say here? Oh, right. That, go ahead.
How are you going to force?
Yeah.
G
well, I was just going to try to give D, I was going to impose on D some sort of surjectiveness constraint. But in order for that to work, you need some sort of subjectiveness to make sense in the doctrine. So, you know, if we were just talking about Cartesian products or something, then we didn't really have a notion of surjection there, as far as I can tell.
So you need some co-limits a little bit.
Perhaps that's what's going on here. So yeah, I'm right. So I'm making things precise enough here that we can see where I'm being a little bit imprecise. That we really need. It seems like we really need something here. And
what?
I think we should say that it's an epimorphism, but I think we should say a little bit more than that.
A regular epimorphism. Is there like some particular thing that it co-equalizes?
It's something like that. It's something like that. But but I certainly am being a little bit sloppy here. This is, you know, we're trying to show the way that you could do things rigorously here, but there is a little glitch here that I'm.
What about the other option, which is just like not fix this? Like, what terrible thing happens if you allow?
Then every group has one extra torsor, is that right? Which is this.
Yeah. But
is that the only thing that happens? Well, or no, it's not just that, because in the varying case, you know, you could have this whole family of torsors, one for each component of your scheme or something like that. But each component gets to decide separately whether it's going to be empty or a genuine torsor. So somehow that's annoying. I think there is in this doctrine that we were talking about, this doctrine of two rigs, very nice two rigs, you can express the idea that the displacement thing should be surjective in a good way. But you know, there's fine print in that in a good way thing. But
it is sort of surprising that it's like,
yeah,
like this super beautiful notion that you just described.
Yeah,
it turns out to be the one that you decide you don't want to use. I mean, it almost makes me think that like the annoying things that make you tack on this extra clause to the definition, maybe they're less annoying than the fact that you have to tack on this.
That could be, but it could easily just as well be that I'm just, you know, that I'm just screwing up here, that there is some beautiful way to
You'd think that if it was like, if the real right definition excluded the empty torsor, that there'd be some really nice way to state the definition of a torsor.
Well, yeah, I mean, but there very well may be. It may be just that I'm, you know, doing a bad job of making it sound.
Yeah, well, it's like you think like a local maximum of elegance, but then it's like not the.
Yeah. So one of the things that we're seeing here is, right, there's an actual theory here. I mean, what we've been saying should make us want to have a theory. And again, this could be theory in various doctrines, right? I mean, this theory, the doctrine that we were implicitly using here was less specific than the doctrine we're supposed to be using in algebraic geometry with these symmetric monoidal locally presentable categories or whatever. But whatever, whichever doctrine that we're working in here, this should make us probably want to talk about a theory where we don't nail down the group ahead of time. Actually, and this is actually related to what you were saying. right, because we have a theory, right. I mean, there's a level slip here, right? There's the theory of a torsor of a particular group, but on the other hand, this idea of the theory of a group without identity element, a group with movable base point, and that's the theory that's maybe sort of wants to have this admit this empty model as well, or something like that. I don't know, but right. So there's right. There's some sort of theory where we we say the theory of a group object G together with a G-torsor X, and you define it in this way. And so there's a syntactic category for that. And right, so that if I'm not screwing up here, if you just kind of query that in a kind of high level way, that is sort of like saying we would be dealing with the, depending on how you do it, it would be like the representation category of the generic commutative Hopf algebra. I think that works out to be the same thing. So that, right, I think that's what I'm saying. There's a generic commutative Hopf algebra, and it has its representations, which kind of live over the universe where it lives, I think. And yeah, and that would, right, that would be, a theory with these two object variables, G and X, where G is a group object and X is, or a commutative Hopf algebra object, or whatever you call it. And the X would be a torsor object. And then,
so could you also describe it as just like the theory of a group object and a torsor of it or maybe
yes, I mean that's what I was trying to say. Yeah.
Hopf algebra and a torsor of it.
Yeah.
So they're both generic. Yeah.
Yes, they're sort of generic. Yes.
Yep.
Yes. Okay. And then, right, and then if you have a specific commutative Hopf algebra, then you have this interpretation which specializes the generic commutative Hopf algebra to this particular commutative Hopf algebra, and then then you're dealing with well, and then you work all this out, and you find out that, right, you find out that if you start with this very abstract theory of a group together with a torsor of it, the syntactic category for that theory, and then if you sort of force belief in, by the way, that really is forcing, but I'm not going to talk about that right now. If you force belief in that generic group being a particular group, and you look at what the resulting syntactic category is, you'll discover that resulting syntactic category is the representations of that group, or more precisely, the co-modules of that commutative Hopf algebra.
For some reason, I've never done that, or I'll tell you what that is in a second. So one thing I never seem to have done, or don't remember ever doing, is taking a theory and then
I'm not sure you haven't done it, but go ahead.
Yeah, well, that's what I'm wondering about. Could I have secretly done it? So,
right.
But anyway, it sounds like you know what I mean, but I'll say it anyway for the people who don't have telepathy who are watching this. So, take a theory, it has a couple of objects in it, and then I take a model of the portion of the theory that involves one of those objects. So that's making that one be concrete and specific, and then sort of I get a new, somehow push forward the whole theory, so that now that portion of it has been made specific while the rest remains unspecific.
Yes, in other words, what you're saying is it's just a categorification of the general process where you have a presented commutative ring or something like that, and then with some abstract variables, and then you specialize those abstract variables to some particular number. You know, you specialize one of those particular variables. You call a parameter or something like that, and you specialize that to a number.
Yeah, yeah.
And,
So
and you're just categorifying that process using these two rigs instead of the rigs.
Yeah. But I've never, anyway, I like this idea a lot. So like start with a generic group and it's generic.
Yes.
Torsor, then you make one of them, make the group be a specific one. Then you get this specific category, which in this algebraic language, like you said, gives you this category of co-modules for a specific commutative Hopf algebra. Okay, that's cool.
Yes. Right. There's so many details that I'm blurring it. I mean, one of the things we didn't say was that you know, when your group is an algebraic group, and you're expressing this in the doctrine that we like, that the torsor X itself has to be a, well, I was going to say a commutative algebra, but in more formal language, a commutative tensor monoid. So, you know, because G itself is also, right? I mean, G itself is a commutative Hopf algebra. So in particular, it's got an underlying commutative ring, and X also has an underlying commutative ring, or, you know, I'm being sloppy here about whether I'm calling this a group object or a co-group object, right? Or a co-torsor object. I guess the commutative ring is the co-torsor object or something like that.
Yeah.
But geometrically, the torsor object. And yeah. So so where are we? So right. It's also fun to think about what is the actual syntactic category of various things that we've been talking about, right? To work out it in some relatively gritty way. What does the syntactic category look like for, you know, the theory of a commutative Hopf algebra in our doctrine or something like that? Or even just the theory of a commutative algebra. It's fun to work out. I mean, that is like very simplicial in nature, I think, right? I mean, it's, well, the theory of a not necessarily commutative algebra, that's very simplicial. But then if you add the commutativity, it's still simplicial, but it's got something extra. And then if you make it Hopf, that makes it sound like there's some extra layer of simplicalness or co-simplicalness on top of that. I don't know, but these are definitely fun things to work out. And not just fun to work out, but it makes me suspect, probably makes you suspect that, you know, we might, in doing this kind of thing and working out these syntactic categories, we might find that we're reinventing various kinds of complicated algebraic apparatus.
Yeah, certainly the simplicial stuff associated to the fact that the walking monoid is the augmented, is the opposite of the augmented simplex category. No, it's the augmented simplex category. That stuff sort of like makes me think of like group cohomology, and
it makes me think of Hochschild complexes and stuff like that. But I could be off base with that also. But I think it's something like that. So yeah. So where are we? We're well, right. We're trying to get to very concrete number theory stuff, but we're having too much fun with the very abstract stuff.
It's okay to do a bit of fun.
Oh, right.
There was, so the sort of more nitty-gritty problem that we were running into was, like if we pick a particular group, like Z mod 2, but maybe like a more general group, and then we look at its Hopf algebra, and then try to understand the category of torsors of that in this language, in torsors in vect, for example. Like what do we actually really get, right? So we kept stumbling over exactly what it was. And
yes, and we want to do a lot more of that kind of stumbling today, because I don't have really beautiful, definite answers. Like for example, I really want, I think Z mod 3 is a really good example, and I'm still stumbling over it, but I've made a bunch of halfway interesting progress that I'm hoping I'll really get to that before we.
So I'm hoping what I'm
Yeah,
hoping to do. I mean, this may be optimistic, but I'm hoping what we do is like a clear but abstract description of the category of torsors over a field for some finite group, for any finite group. So, and then
I mean, there's all sorts of restrictions we might put on that to make it easier. I mean, even just asking for that to be a finite abelian group.
Yeah, sure.
That might be a very nice halfway house on the way toward.
But
we're really interested in the non-abelian ones too. But yes, it might be good.
I'd like to
Yeah.
So if everything proceeded systematically, I'd like to get that sort of solidly nailed down, so that then when we try to do it for something like Z mod 3, we'd know exactly what it was that we were doing.
Sure, but we may alternate between the general case.
As I said, it's optimistic.
Particular case and vice versa. Yeah.
I know. I was saying that's what I would like, because I know that's not going to be how it's going to happen. More like,
well, it's going to be give and take. It's going to be give and take between
what the question was.
Yeah.
Right. Okay.
Well, but okay, but again, let's emphasize that in understanding what these torsors are, that we really do want to shift back and forth between some very general abstract ways of thinking of it and some very concrete particular ways of thinking. Even in this Z mod 2 case that we've already used as a starting point in last week's discussion, even in that case, we can see that there are some very different viewpoints we can take. We can take, right, if we really think of it as an instance of this torsor concept with the displacement thing and all that. Then it sounds like there's a lot of stuff in there, right? We have this whole co-torsor object, which is a commutative ring, and then we have this commutative Hopf algebra, and then we have this co-action of the commutative Hopf algebra on the co-torsor, and then we have the co-displacement thing or whatever going quasi sort of inverse to the co-action. That makes it if you work it out that right way, it makes it sound very rigorous, and it's also conceptually clear, but it's just so much stuff in there. And then in addition, you just specialize it to Z mod 2. But it works out to be something amazingly simple. So am I saying this right? So what kind of thing? Right. So one of the things we want to say is that a Z mod 2 torsor really just works out to be, well, right, even in this case, there are complications, right? If you do it over the integers, or if you go even, over, even without numbers, if you just do it over the category of sets instead of the category of abelian groups or something like that. But if you do it over the integers, you already get some tricky things, which I think we actually mentioned a couple of weeks ago. But if you do it over the rationals, then it becomes nice and easy. Right, because the representation theory of Z mod 2 is easier over the rationals than it is over the integers. Over the rationals, it sort of cleanly splits or something like that. Everything is just.
I'm getting so like.
Right. Over the rationals, you just every involution, every involutory linear operator just cleanly splits into two different it splits the vector space into two different eigenspaces, the one eigenspace and the negative one eigenspace. Whereas over in a abelian group, that doesn't happen cleanly. You get right over the prime two, funny things happen or something like that. You don't get a
Can
clean.
you remind me? It's
What?
also, yeah, it's clearly the prime two that's bad because that's what you use to
That's right.
formulas for the item potence from the Z-mod 2 action.
Right. There's probably some fancy thing that
But what can you
supposed to
remind
say
me?
that
Like,
this
what,
group is ramified over the prime two or something like that, but I don't worry about that. Go
yeah,
ahead.
yeah. Well, okay, sorry. But can you
Yeah,
just
go ahead.
give me there should be some easy example of like a abelian group with a Z-mod 2 action that is sort of not
Yes.
a sum of a
Yes. Yes.
fixed group and an anti-fixed.
Yes. And again, we did kind of give this example previously, and I don't know exactly the right way to say it, but it's something like the difference between a chessboard and a checkerboard. So what kind of involution are we talking about on a? It kind of doesn't even matter whether you use the chessboard or the checkerboard as the.
I don't even know what the what's a. Okay.
Well,
Okay.
what I mean is, the
thought-
checkers aren't allowed to go, or bishops versus
Uh-huh.
or something like that. The checkers or the bishops are constrained to the, the real spaces in the checkerboard are not the 64 of them. It's just the black squares, like or the red squares or the whatever it is. So.
Okay, but can you just tell me?
Well, I'm saying it's what right? It's just like let's say it's the chessboard that has these two axes. Right? I mean, there's
So you're thinking of.
You take an infinite chessboard and you like flip the X and Y axes or something like that. But if you do that same thing to the checkerboard, then.
So when you say flip them, what do you mean? Switch them?
All right. So, okay. Maybe I should try to draw a picture here. Do I still have the screen thing here?
Yep.
All right. Let me see.
Yeah, sorry, it's coming back to me. But
all right. So yeah. So let's see. So my screen is a chessboard, roughly speaking.
yeah.
And so let's take like the horizontal to be the eigenspaces, to be the positive one eigenspace, and the vertical to be the negative one eigenspace. So I guess that means that the involution in this case is flipping things vertically.
Okay.
But that still exists as an involution on the checkerboard. If I only take every other vertex or every other square or something like that,
Okay. Okay, good. Okay.
I mean, there's cleaner ways of saying it, but this is my way of thinking about it. It's the difference between a chessboard and a checkerboard.
Okay, so for the I feel like I want to talk to like some imaginary audience who's like going, what?
Sure.
So
sure. Yeah. Figure out a good way to say
it
it.
might actually just be me, but I have this feeling that like other people are like even more confused. So
I mean, there's a good way to say it here, but I didn't necessarily. I just gave
yeah. So I'm going to try
a way to say it.
What Jim might be saying is, I'm going to like focus on the checkerboard. I'm going to call that Z squared. So as an abstract group, that's Z squared. And so there's a involution on Z squared, which is in those terms, well, that Z squared are the red dots here, and the involution is a vertical reflection for the mathy type people out there. So if you think of the red dots as z squared, that involution is sending.
Let's pick out an origin here.
Yeah. So that's sending like 1, 0 to 0, -1. And it's sending 0, 1 to -1, 0. So this is some involution on z squared, which doesn't have, well, it has a one eigenspace, it has a one eigen group and a -1 eigen group, but those two groups, if you take the direct sum, you don't get the whole original group, you just get a subgroup of it, so it's like, yeah, so the so the group is not a direct sum of the one eigenspace and the -1 eigenspace.
Yeah, or there might also be a useful way to express it in terms of something like that the eigenspaces are different from the co-eigenspaces. Or something like that. But yeah, that's the vague idea. Yeah, and I tried to draw in those eigenspaces.
Okay.
Eigenspaces.
Yeah, that's why I felt compelled to think about that for a bit. But okay, so we're gonna not worry about that because we're gonna work over the rationals. Is that the plan?
That's right. That's right. That's right. It may very well, we may return to this kind of thing where we work over a ring instead of working over a field. And I used to think about that a lot, but I think I really missed out on learning interesting stuff that you can learn by just thinking about fields. So we're simplifying things for ourselves.
I think it's characteristic zero. That's what's really helping us here right now. Yeah.
Oh, that's interesting. That's interesting.
Characteristic not two. I mean, yeah. So this. Yep. It's something like the.
I mean, obviously, right?
Z mod for the group Z mod and its representation theory would get funky over fields of characteristic P if P divides N. There's like,
so, right, and obviously it's getting interesting in a sort of number theoretical way, but perhaps too interesting. If we stick to working over the fields, then there's still enough interesting things going on number theoretically. Avoiding those other number theoretic complications may actually help us to focus in on some particular thing that we can understand, maybe. So trying to avoid these complications, think about the nice simple case of the representation theory of Z mod 2 over the rationals. We have this very abstract definition of what a torsor is. It's very involved, but we work out in this particular case, and we end up saying, am I saying this right, that a Z mod 2 torsor is really just, over the rationals. And when I say over the rationals, it means, over the rationals or beyond, over anything that incorporates the rationals. So over the rationals, a Z mod 2 torsor is don't tell me, it is a line object together with a trivialization of its tensor square. And if you don't like that language, then that might sound scary. But actually, this is a very nice thing to say in this. If you understand this language of line objects and so forth, then this is a very nice, simple thing to say. And
also, you could say, we mentioned this before, you could also just say it's an object together with a trivialization of its tensor square.
I guess that's right.
Forces it to be a line object. So
that's true, but that is a good simplification for certain purposes. But it's for other purposes. It's also good to know ahead of time that it's a line object because they're very easy to deal with or something like that, even when they're not of finite order.
So let's see. So
yeah.
So like if we do Z mod. So what what I'm confused with about is that it seems like there's something that you could generalize that concept to any group, and and I'm not sure that would be the. I think I'm getting the sense that that's not the right generalization, but I'll just say it, which is that you can like take a finite group.
That's a very interesting idea. Go ahead. Yes.
So take a finite group and then take a line object for each group element.
Yes.
It's like a line bundle over the group, and in some abstract sense. And then
I mean, it's a homomorphism from your abstract group to the sort of group of line objects.
Okay, I wasn't done saying what I was going to say, but you finished it off. Yeah. So,
but I mean, right, but it's probably strongly a homomorphism or something like that, because you have to, you can't say that the equations are preserved as strictly as equations, but they're preserved in a good.
Yeah. So it's like a weak or strong
yeah,
from the group to
strong, meaning that it's weak. Yes. Or
to the group of 8. Yeah. Group of line objects, the 2 group of line objects. So that's a sort of nice kind of thing, and I know a bit about that type of thing, so that like I could guess that like I could figure out how you like classify those in terms of cohomology of the group with coefficients well, I could do it in some more concrete case when we're talking about when our line objects are like one-dimensional vector spaces over a field. Then I would say it's classified by H2 of the group with.
Yeah, you're probably right. Go ahead. Yeah. Go ahead.
H2 of the group with coefficients in the group of units of the field. So now I'm looking at. And I bet that must generalize to like the more abstract context that you started out talking about. So that's a really nice little subject, because you can get, different interesting ones.
Yes. Right. And the question is that what we want? And if it's not what we want, why isn't it what we want? And it's sort of very close to what we want, but there's some funny issues of Fourier duality and very abstract forms of Fourier-Hopf duality and things that are intruding here. And that's kind of a big part of what we're trying to clarify here is how close is what you said to being the right answer?
I mean, it sounded from what we said last time that it's going to be the right answer when your finite group G when your finite group G, when all of its irreducible representations are one-dimensional, so you should only really expect that when G is abelian, but even when G is abelian, it's not good enough, unless you're working over a field of like algebraically closed field, like the complex numbers. So anyway, so this is like why Z mod 3 was going to be harder, because not all the irreducible representations over the rationals are one-dimensional. So somehow or other so what I'm confused with is like, what's the thing to say for the general case that's sort of concrete, like what I had been saying was sort of concrete, but like handles examples like Z mod 3 over the rational. So anyway, this is what I said before is like, I would like to know what it was, this thing that we're trying to understand here.
Yes. Well, I'm not going to give you really clean, great answers to that today, but we're gonna try for that. We're gonna try for stuff like that. We're gonna see how it goes. But so, I mean, right, one of the things that's going on here that I don't think you quite said it out loud, but maybe you're thinking it, I don't know, maybe you weren't thinking that, right, I mean, we're sort of used to the idea that, for example, a finite abelian group is isomorphic, though unnaturally, to its single Fourier dual. Like it might be naturally isomorphic to its double Fourier dual or something like that. So I mean, and that whole issue is sort of intruding in here, right? The sort of possible unnaturality of the isomorphism to the single dual. That was sort of halfway implicit in what you were saying. But also, I mean, right, I mean, in the sort of algebraic context, things get even trickier, right? That what am I trying to say? That like the Hopf dual of a discrete finite abelian group is actually like of Z mod 3 is actually, if you work out what the Hopf dual of that is, and the Hopf dual is sort of like the algebraic version of the Fourier dual, sort of in this context. I'm not sure exactly what I'm saying here, but if you work out what the Hopf dual is the Hopf dual of the discrete algebraic group Z mod 3, it's not another discrete Z mod 3. It's actually the group of cube roots of unity, which is not quite the same thing. That's not quite a discrete group, right? Because of the way that funny things happen over certain finite fields and things like that that make that different from. Well,
funny things happen over infinite fields too. I mean, funny things happen over fields of characteristic 0. That's what they still, I mean, cube roots of unity can be.
yes, that's right. Over the rationals versus over the reals, or over the complex numbers, or over the algebraic numbers, or something like that. Right. That's right.
So yeah.
So
that's what it is. That's how you should think of the dual, is that it's the
I mean, we may have already done that calculation at some point, but you should certainly do the calculation for yourself, and maybe we should do the calculation together here at some point. You know, just working out what the Hopf do. I mean, we probably secretly have done this calculation, but I mean, really work out how the Hopf dual of a commutative right. If you have a bicommutative Hopf algebra, you can just if you have a finite dimensional bicommutative Hopf algebra, then it's pretty straightforward to talk about the Hopf dual of that. But when you do that, you'll find that funny things happen, in terms of shifting between the roots of unity and the discrete cyclic groups. They are sort of dual to each other in this Fourier Hopf way.
That's weird. Yeah, it's just weird that I never thought about that. That just somehow
I mean, that's somehow really important in disentangling all this basic reciprocity laws and stuff like that. I think, if I understand correctly. So, okay, we're trying to make further progress today. And I'm still struggling to remember how we're supposed to do this. Well, okay, so a big part of the point is that, the case of Z mod 2, avoided this, right? Avoided that. I mean, Z mod 2 was easy because the square roots of unity are already there even when you're over the rationals. Z mod 3 is already tricky because the cube roots of unity are not there over the rationals. So this is like a good challenging toy case. It's not too challenging, it's a toy challenging case. But if we can, really make progress on understanding this case, then that might be really good in terms of understanding more challenging cases. So yeah, that's what we're really trying to do here. So we're really trying to try to do for Z mod 3 what we've already done to a great extent for Z mod 2. But taking into account the fact that, we're going to have some things got to get trickier. Some things are trickier here, but we're still trying to do the same things that we did for Z mod 2, but do them for Z mod 3. But just, we know there's going to be complications. So what am I going to try to say here? Okay, so let me, I still think we have enough time left to do some fun stuff, but I'm fumbling around here. Let me go ahead and see if I can do stuff here. So let's try to think about, yeah, so we've got this particular syntactic category that we're very interested in. And we're really interested in interpreting this syntactic category into other syntactic categories. So yeah, so this syntactic category is formed by the rational vector spaces equipped with don't tell me, with whatever you call them, trivolutions or something, not involutions, but things of order 3. Trialities or whatever you call them. And right, and right, so you sort of want to Fourier dualize and just say that we've got these 3 eigenspaces. The one eigenspace, what I'm trying to say, one to the 0/3, and 1 to the 1/3, and 1 to the 2/3. This is what we want to do, but we can't do because we don't have these cube roots of unity already in the field. So, but we do at least have this, right? This one is there, right? And the other 2 are kind of indiscernible from each other in a Leibnizian sense. And so what does that mean? That means, right, that means that this representation category is what we might call, loosely speaking, a rational 2 vector space, where it's got sort of like 2 basis elements, and each basis element is, from what we've vaguely talked about in our previous discussions when you were teaching me about the 10-fold way, we were thinking about these, well, you were telling me about a lot of division algebras and very general abstract context, but we were thinking about how this related to 2 vector spaces, like for example, real 2 vector spaces compared to complex 2 vector spaces, and how the idea was that you would have basis elements, but basis elements would be colored by division algebras. Is that right? Colored by division algebras.
Yeah, they're endomorphism.
Okay, but somehow I'm not quite sure why it. Oh, I guess I guess what's happening here is that they're actually being colored by commutative division algebras, because we're only looking at representations of abelian groups. So somehow that's simplifying things, I think. Don't try to press me too hard on this, but I think somehow we're in some pathetically easy case where we don't even have to think about non-commutative division algebras. We just have to think about commutative division algebras over the rationals. So those are basically, number fields.
Yeah.
Something like that.
Yeah. Just number fields. Yeah. Well, they're not.
Yeah. I mean, we probably don't have to worry about infinite dimensional stuff. So, I mean, it really seems like this one is, the most vanilla kind of thing, the commutative division algebra. I mean, right, what I'm saying, what we're saying that these, I don't know, I have this horrible mental image of like a chromosomal disease where 2 of the chromosomes stick together or something like that, right? I mean, these 2 irreps that are supposed to be 1-dimensional, they're sticking together into a 2-dimensional irrep. And that's giving.
And what's its
commutative division algebra? What is its endomorphism algebra as a commutative division algebra, as a number field? I think it is the Eisenstein integers, I think. I mean, did I really work that out? It seems very plausible, right? That this is right. So what is this? This is Q.
Yeah. Okay, that sounds
so
good.
The endomorphism algebra of the trivial representation is just rationals as a commutative division algebra over itself, and this other one is
Yeah.
Like that. The Eisenstein rationals, the Eisenstein number field.
I think that's right.
And right, and we we are short on time here, so that makes me, that gives me all the more excuse to just be really sloppy here. So
Okay.
there's really interesting stuff going on here, but there's not enough time to be careful about it. So what am I trying to say? So I think, well, first of all, I need some name for this syntactic category. Should I just call it T, maybe? So we're interested in like models of this syntactic category into like the category of rational vector spaces, for example. Or, but we're interested in models in more exotic universes as well. And right, we're I don't know, right? We're based on vague rumors about cubic reciprocity. I'm sort of guessing that if we took models of this where the models were themselves over the Eisenstein integers, so it'd be, vector spaces of the Eisenstein integers. In that case, I'm vaguely guessing that things would be a lot like the way it was for the Z mod 2 case. And maybe it would be, I mean, we were talking around about cube-free integers and stuff like that. The idea that there would be just some cube root that you were taking of something that was giving you like, right, there was some trivialization of the third tensor power, and that would correspond to taking the cube root or something like that. Something like that. I don't know.
That's the sort of,
yeah,
that's sort of like the thing I was talking about line bundles over group. That's sort of like the paradise.
That's right. So like, when I was struggling to learn some basic number theory for the first time, people would say things like, well, if you want to learn cubic reciprocity, it doesn't really work well unless you do it over the Eisenstein integers or something like that. You can't really state it in a good way or something like that unless you work over that. Whereas now I really have the opposite viewpoint about that, right? That we really want to state it in this better way that doesn't rely on this simplification of working over the Eisenstein integers. But somehow, right? I mean, so somehow what it's going to be is that when you don't work over the Eisenstein integers, the problem is itself going to bring the Eisenstein integers with it. So somehow the Eisenstein integers are actually so deeply embedded in the problem that even if we're not working over the Eisenstein integers, we're going to work with them anyway, because we're going to work with them formally. We're going to start working with the theory of an Eisenstein integer or the theory of a vector space over the Eisenstein integers, things like that. I mean, the problem is really going to force us to think about the Eisenstein field. But
so those other guys were just like knuckling under to the pressure and saying like, forget it, we're just going to work over the Eisenstein integers from the very start.
That's the way it sounds like. That's the way I interpreted it. But they may have actually been doing something more sophisticated that I didn't really understand. But at this point, yeah, we really want to. There's something interesting to be learned if we really try to do cubic reciprocity, but don't do it over the Eisenstein integers, but do it over the rationals themselves. I mean, I'm not sure I'm stating that.
Another way to say what you're doing so far, we haven't really gotten to the reciprocity part, but what you're doing so far, it's sort of like, let's do Fourier analysis on a finite abelian group, but not over an algebraically complete field. Do it over the rationals and then see how that gets more fancy than what we're used to from.
Yeah, or as people might call it, harmonic analysis. Usually the excuse for having higher dimensional representations is that you have a non-abelian group. But here we have some different excuse for having higher dimensional representations, and it's just because the field isn't algebraically complete.
So that's
so So yeah, we're interested in this syntactic category T, which is roughly speaking, just as a category enriched over rational vector spaces. It's a so-called rational two-vector space with one basis element colored by the rational field itself, but with this other basis element colored by the Eisenstein field. And right, and I think I at least have time to get one punchline in here. So what I want to say is something like this, that there's some interesting theory interpretations that are going like this. Sorry, I have so much trouble with this. There's something going into T from some other theory. I mean, maybe I should call this T. I mean, I should call it T stands for theory or something, and I'll say the theory of a Z mod 3 torsor. And hopefully it's clear what algebraic group we're talking about there, what affine algebraic group we're talking about there.
That's the same T that you were talking about above, right?
Say that again?
That's the same T that you were.
Yes, that's the same T, but I'm going to have multiple T's, so I'm decorating the T's with different. So we're going to have, what am I going to try to say here? We're going to have the theory of a line object L over the Eisenstein field. I'll write it this way, the Eisenstein. I mean, I'm conjecturing that this is the case. What I'm conjecturing is that whenever you have one of these representation categories, so it's like a two-vector space, but the different basis elements have correspond to different commutative division algebras, also known as fields, right? Commutative, something like that. Different commutative division algebras. I think if we work out what that's really saying, I think that's saying that basis element is, well, right, okay, so now it's really going to be a representation category. So it's really going to be, right, now I want it to be not just an abstract two-vector space, but I want it to have a tensor, a nice commutative tensor product on it, a nice symmetric tensor product on it. And also, I want it to be like a group representation category, so there should be duals. So even if I have an object that I'm not sure it's a line object yet, I know it's going to be it's going to have a dual. It's going to have a dual. But what I'm conjecturing here is that just by knowing what the commutative division algebra is, that I think that that's actually giving us not a line object. It will give us a line object only if the commutative division algebra is the base field itself. But if it's giving us some other commutative division algebra, and I have to be careful with the language here, that is giving us a line object over the Eisenstein field. Now, what do I even mean by that? I mean, it sounds like I'm saying something tautological, but I'm not quite saying something tautological. I'm saying something that should be sort of interesting. So what am I trying to say? I'm trying to say that in the doctrine, we can articulate the concept of an invertible module over the Eisenstein field. So, right, I mean, so, right, we're in our usual language where we can say stuff using, tensor product and co-limits and everything like that. And I hope, if I'm not screwing up, using that language, we can express what the idea is of being an invertible, a relative invertible module. So what am I trying to say? We're trying to express the idea of saying, so let's have, right now I'm sort of trying to sketch out this theory here. What do I mean by the theory of a line object over the, so I'm trying to articulate what I mean by that. I'm trying to parse this concept. I mean, right, it's using very informal language, but we're trying to put it in more formal language that we can recognize as parsing in the doctrine. So what am I trying to say? We're going to have, right, so L is actually going to be a two-dimensional object. Right, the line object is supposed to be one-dimensional, but here it's only relatively one-dimensional. So it's, but right, the underlying ordinary object of this Eisenstein line object is going to be a two-dimensional object. And what is it going to have? It's going to have I mean, right, right, there's some work that you can put into expressing how to say two-dimensional. We thought about that, and we could sweep that under the rug for the moment. But in fact, we might not even need that. Maybe we can just say that L is an object, and let's call it the formal Eisenstein inverse of L is another object. Yeah, so I'll kind of cross out. We don't even need the two-dimensional. I'll just say that these are two objects. And now I just want to say that they're inverse to each other in the Eisenstein way. So what do we mean by that? So we want to say something like that. L tensored with L inverse over the Eisenstein field should have an isomorphism. Let's call it I don't know, A or something like that, to the Eisenstein field.
So in any of these symmetric, monoidal, ugly, presentable, k-linear categories, you can define objects that act like your favorite well, sorry, I said k-linear, but I mean q-linear. So yeah, in the categories, you can define objects that basically just act exactly like your favorite algebraic number fields.
Yes.
And you get to use them.
I mean, it's like, again, in the decategorified case, this is the analog of like if you have a commutative ring, it's got all these fancy elements in it, but it's got the good old numbers in there as well, right? In any commutative ring, you've got 1 and 7 and 19 and so forth.
Yeah.
And yeah, we're just importing these constants from outside. That's right. That's right.
You have to.
That's. I think that's vague. That's old-fashioned programming language jargon, importing concepts.
Yeah, I like that.
Go ahead. Yeah.
So do you have to assert that L is a module of Q Eisenstein before you can go and write that left-hand side?
Yeah, that sounds right. That sounds right. But that parses in the doctrine. You're right.
Yeah.
So right. So as you say, you have right. So right, we are interpreting this thing as an internal thing. It was external, but the external things get imported to become internal. And so we can talk about it as just another thing in the doctrine. And then, as you say, we should have some action of it. So we have L tensor the Eisenstein thing mapping to L or something. And this is an action. Call it B or something like that. And yes, and
this is so much.
Say that again.
Yeah, it's funny how this is exactly like the two things you wrote down are just exactly like. No, they're not exactly, but they're so much like the definition you wrote down of torsor at the very beginning of this conversation. You have this thing.
Yes.
Thing acting on it. This is not a division. Right, it's different though, because the second map is not from L tensor L to Q. It's not a distance map. It's a
But at some point it may be, we're not doing that yet. But we may very well feel that we want to do that. I have a feeling that we are going to be dealing with.
I guess in the Z mod 2 case, we would have had that too.
Yes, but it wouldn't have helped us in the Z mod 2 case. But I think my vague guess in the Z mod 3 case is that we're actually going to be dealing with a Z mod 3 torsor. I think we're going to end up thinking of as a Z mod 3 torsor over the base field as being a Z mod 3 torsor over the base field augmented by the Eisenstein. And then equipped with something else. We may secretly be using the method of descent here. I'm not quite sure yet. Yeah, I mean, it sounded like you were hinting at something there, and you were commenting that we're not really doing that. But I think we may eventually be doing something like what you were hinting at. But anyway, let me try to keep going a bit here. So yeah, we can parse what it means for this imported external thing that's now internal, this QE Eisenstein. We can parse what it means for that to act on this L, so that L is at least a module of this external thing. And then we can also parse what it means to, tensor over this Eisenstein thing. That also parses in the doctrine. And I guess the person who taught me about that was Jeff Egger, I guess. So what am I trying to say? That it was something very straightforward. It was like, what am I trying to say? If you tensor, how does that work? It says if you want to tensor V and W over A or something like that, then it's like you're doing, don't tell me, it's like you're taking the ordinary tensor product of V and W, but then you're like taking some co-equalizer. So it's something like V tensor A tensor W. And like one of these is like a left associativity, and then another is a right associativity or something like that.
Left action and right action. But
Yeah. It's like,
that's
that
right.
way you go through. Yeah. And if you do that the right way, this is what I think Jeff Egger taught me about how to get these relative tensor products to parse in this doctrine. And so you can do that, and so so the whole idea of being invertible under the this relative tensor product that parses in this doctrine. So yeah, so this works. And I'm right. I'm sort of blurring the distinction between being a line object and being an invertible object. I forget right there. Subtle differences in the definitions of those, depending on whether the symmetry is like supersymmetric or non-supersymmetric or something like that. But it's okay. That's something we can just be sloppy about the moment. Being a line object is almost just like being an invertible object. So I'm giving you some idea of how to get this to work. So okay, but now, right? So this is something we can do. But on the other hand, it's also very important. It's also very good to notice how this is sort of a categorification of the kind of thing that we do in like synthetic differential geometry, where we have like this walking infinitesimal tangent vector, which we sometimes call D, and we have like a smooth space X, and we're in a nice enough category that we can take an exponential X to the power of D. And this even works in some algebraic geometric contexts that you can have, you can interpret the walking tangent vector in an algebraic geometric context as being this, sort of thing that violates the Nullstellensatz or something like that. It's got the nilpotent stuff in it or something like that. And, those little nilpotent things, even though the category of algebraic varieties is like so completely far from having exponentiation of all objects, it does have, you can treat as exponents these little tiny infinitesimal objects. And, ideas about synthetic differential geometry, coming from Lovier and coming from other people, coming from Grothendieck and so forth, are Lovier really explained a whole lot about how to think of this in terms of exponentiation in nice categories. And we're doing a categorified version of that here.
What are we exponentiating by whom?
All right, let me see if I can get this to work. So I guess we're saying that the category of vector spaces of the Eisenstein field, that the spectrum of that 2-rig is one of these sort of infinitesimal exponents in this in this world of categorified algebraic geometry that we're doing here.
Yeah. So when you I'm very confused, but I'll just say exponentiate some theory by it. What do you get? You stick in these internal Eisensteins into your theory. Is that what? Yes. I mean, something like that. This is certainly worth talking about. We should really already there. Well, yeah. I'm just a little bit worried that I'll get the exponentiation mixed up with the thing that it's adjoint to and things like that. I mean, it's what we're talking about here is really worth doing in a careful way, but not certainly right now when we're sort of running out of time. But I mean, we really do want to, clarify eventually how some of the things we're doing here are very nice categorifications of the kinds of things that Lovier and other people do when they, treat little nilpotent things as exponents. By the way, and I think, I hope I'm not screwing up the history of this, but I think actually, if you go back much further before Lovier, I think he was taking the spectrum of the complex numbers to be an exponent working over the real numbers or something like that. And that's also very much what we're doing, is also very much a categorification of that. So I mean, you're right. You're saying, like, right, there are these little 2-dimensional commutative algebras, and they're all interesting to use as exponents, right? If you take these little nilpotent 2-dimensional commutative algebras and you use those as exponents, then you're basically doing synthetic differential geometry. There's this other very, go ahead. What's the special thing about, why did he say 2-dimensional commutative algebras? What's so great? Well,
these are just famous examples, like the walking tangent vector. If you start doing 3-dimensional ones, then you're doing like the walking higher tangent vector or something like that. But there are these famous ones, the walking tangent vector, it's the, Does this guy study, let's call it the study numbers or Studi numbers or something like that?
Yeah. So, right. Okay. So you're just alluding to how the Studi numbers, the complex numbers, and the split complex numbers are all similar to each other. But
yes. And if if you learned from a certain school, you might have not have thought about using the complex numbers in this context. You might have only thought about using the Studi numbers in this context.
So what are you doing when you're using the complex numbers? Are you just complexifying your variety?
You're doing something really interesting. It has to do with complexification, it has to do with the underlying real of a variety, of a complex variety. And I think this is something that Baez talked about a long time ago. But don't trust me on the history of any of this. I mean, there's a lot of fun stuff here to explore. So we're already way late, but maybe we should try to figure out what time we're actually going to quit, because I still want a punchline. I'm hoping like maybe actually quit at 4:15, or do we have to quit before that?
That's fine. No, that's fine.
Okay.
Making it hard for me to just listen to you because you're like saying these things that.
Yeah, well, that's because I was too discursive in the beginning, and now I'm.
Yeah. Okay, go ahead.
Okay. I mean, there's just so much interesting stuff to really follow up on here, but
yeah, okay, sure.
but so what am I trying to say here? So one of the things that's really going on here, right? There are all sorts of interesting ways that the categorifications are meshing with the categorification and decategorification. The categorified and decategorified versions of these things are meshing with each other. What am I trying to say? I'm trying to say that there's this whole thing, right? I mean, supposing you have, let's say, a commutative Hopf algebra over an extension field of some kind. A commutative Hopf algebra over an extension field, over a field that's an extension of one that you started out with. Mm-hmm. So a simple example is you could have a commutative Hopf algebra over the complex numbers, which is an extension of the real numbers or something like that. Mm-hmm. And then there are all sorts of tricky things you can do with this. Like, what am I trying to say? You could take like GLN over the complex numbers. That's an algebraic group. But you could treat it as a complex algebraic group, but you could also treat it as a real algebraic. And so that's, two different kinds of commutative Hopf algebras, a real commutative Hopf algebra and a commutative Hopf algebra, but they're both coming from sort of
you said
the same algebraic group. Yeah?
You mean a real commutative algebra and a complex commutative.
What did I say?
The second one, you just said commutative Hopf algebra.
Sorry, yes. A real
the
Hopf algebra
complex
commutative Hopf algebra.
Yeah,
That's right. And so they each have their own comodule category.
Mm-hmm.
And those comodule categories, they're both theories. They're both syntactic categories of theories, but they're syntactic categories of different but related theories. And so like, there's all sorts of fun stuff to get. I mean,
you're thinking of them as theories in the doctrine that involves the real numbers, both of them?
Yes. So, well, yeah. Am I saying that?
Because you could also think of them as like theories in different doctrines.
Yes, but I mean, either way you think of it, the one that has the complex commutative Hopf algebra, the first thing that does is it gets you into the complex doctrine. It kind of says, right. I mean, right. It's right. It's something like if you take the real commutative Hopf algebra and you try to say what that syntactic category is, what it's the theory of, it's something like, let me see if I can get it right. It's something like the theory of a torsor of the theory of a bundle of torsors of the group over the spectrum of the ring of the algebra of complex numbers. Whereas if you take the syntactic category that comes from the comodules of the complex commutative Hopf algebra, that's saying, instead of saying that you have a bundle of torsors over the spectrum of the commutative Hopf algebras, it says that you have a point of the spectrum of the commutative algebras together with a torsor, quote, over that point, a torsor of the group over that point. So I'm saying that very badly, but it's this thing this is a repetition of something that we've already seen at the decategorified level. It's like left adjoints versus right adjoints. This is a very Loverian thing. It's like, what am I trying to say? That there are these two differently adjointed things that you can do. You can take the sections of a bundle, or you can take the total space of a bundle. One is like the Cartesian product of the fibers. The other one is like the sum of the fibers, right? The sections is like the Cartesian product of the fibers, roughly speaking.
Yeah.
The total space, that's like the sum of the fibers. So that total space, that's like a left adjoint to the thing going the other way. What is the thing going the other way? Right, the thing going the other way is the process of taking a trivial bundle. Right, the process of taking a trivial bundle, that's just kind of like some extension of scalars or something like that. But you've got a left adjoint and a right adjoint to it. And one of them says, from the bundle, take its sections. And the other one says, from the bundle, take its total space. And that's like the total space, that's like the left adjoint, and the sections is like the right adjoint. And we're repeating that story, but at a very nicely categorified level. So that's what I was trying to say, right? I mean, so the thing is a bundle of torsors over the spectrum of the complex numbers. That's like, yeah, I can't even tell how have we really even categorified at all? Maybe we have. I mean, I know that you do categorify at some point, but that is like right, because we're saying a bundle, that is like the right adjoint thing. Whereas if we say, take a point of the spectrum of the complex numbers, and then take a model over that, that's like we're saying taking the total thing or something like that. So we're taking like a total stack versus a sections stack or something like that. I think we have category already here, but boy, we're really running out of time here. What am I trying to say here? Now I'm just trying to think of desperately trying to think of a punchline to just quit on here. I mean, one punchline is there's a whole bunch of interesting stuff going on here that we need to talk about that we really want to talk about a whole lot more. But do I have any more specific punchline than that? Just to remind ourselves that we're really trying to look at the group Z mod 3, treating in this very, quote, doctrinaire way, treating this very Tanakian way. We're really studying this group Z mod 3 according to this Tanakian philosophy, taking its representation category, which is surprisingly interesting because we're working over the rational numbers rather than working over the complex numbers or something like that. And then we're really trying to take seriously the idea of understanding the torsors of this group. And it's leading us into all sorts of interesting things. I mean, we're already seeing hints that between our different syntactic categories, we're getting some very interesting morphisms of theories going on. And yeah, so I'm sorry, I'll just have to quit right there. But okay. I'm hoping you're getting some sense of what we're trying to do. We started out doing very abstract general stuff, but we're trying to get into some really concrete stuff that's really going to help us understand reciprocity laws and Jugendtram, Langland, et cetera, et cetera.
Yep. Yeah. No.
Yeah.
Yeah, it's good. I mean, yeah. I won't try to say anything more. I mean, there's just a lot of things to.
Yeah, I mean, all the things I was saying in a very hurried way today are things we should try to say in a more careful, more fleshed out way in future times, future discussions. Okay, so thanks a lot. Okay. We're pretty much done here.
Yeah, I think so. I mean, in the sense that, like, there's so much.
Yes, right. I didn't mean really done. I meant we have to quit. Okay, I'll see you.
Yep.
Bye.
Bye.